Next topics which I am going to discuss is, first one is gradient of a scalar field. Following this, we have topics such as divergence and curl of a vector field. Now let us see what is meant by gradient of a scalar field. In order to define a gradient of a scalar field, we have to consider a vector point function in that scalar field, and then we have to consider a scalar function phi. Hence, we define the gradient of a scalar field as a vector of a point in space whose components along x, y and z axis are equal to respective partial derivative of a scalar function phi is called as gradient of a scalar field. If you consider a vector function, that vector function can be resolved into its orthogonal components along x direction, y direction and z direction. It says that here a vector of a point in space whose components along x, y and z direction are equal to respective partial derivatives of a scalar function phi, then such a kind of operation we will call it as gradient of a scalar field. It can be written as grad phi. Since we are considering the scalar field to be phi, a gradient of phi or a grad phi is equal to dou phi by dou x into I cap plus dou phi by dou y into z cap plus dou phi by dou z into k cap. Well, this equation can also be written as dou by dou x into I cap plus dou by dou y into z cap plus dou by dou z into k cap dot phi, or this whole, the partial derivative, the sum of partial derivatives along x, y and z direction can be called as operator del. We can del dot phi. This is called as the gradient of a scalar field. Now, in order to find out the physical significance of the gradient of a scalar function phi, so let us consider a three-dimensional space, and in the three-dimensional space let us consider a point P with the position coordinates x, y, z, and very near to it let us consider another point Q with the position coordinates x plus dx, y plus dy and z plus dz. Now, let a vector dr be joining the position coordinates P and point Q given by dr is equal to dx into I cap plus dy into j cap plus dz into k cap. Let us consider, let phi be the scalar function at P. Okay. So, we have considered a point P where we are considering that phi be the scalar function at the point P, then phi plus d phi be the scalar function at Q. So, if we consider phi to be the scalar function at P, then we will consider that phi plus d phi is the scalar function at the point Q. Then the rate of change of phi is equal to d phi is known as the total differential of the scalar function phi, which is given by phi is equal to d phi, nothing but total differential, which is given by d phi is equal to dou phi by dou x into dx plus dou phi by dou y into dy plus dou phi by dou z into dz. So, this is the total differential for the scalar function phi over d phi, which is given by dou phi by dou x into dx plus dou phi by dou y into dy plus dou phi by dou z into dz. This equation can also be written as d phi is equal to dou by dou x into I cap plus dou by dou y into j cap dou phi by plus dou phi by dou z into k cap dot dx into I cap plus dy into j cap plus dz into k cap. Right. Now, this equation of total differential of d phi can be written in that way also. Now, we can write it further. D phi is equal to, the whole equation can be written as del phi dot, you know that this is dr, because we have written the equation here dr, vector dr is equal to dx into I cap plus dy into j cap plus dz into k cap. That is why the equation here, which can be written as, now del is the operator and phi is the scalar function. So, d phi is equal to dou phi dot vector dr, or else this can also be written as dou phi is equal to del phi r cap into dr, or this can be written as d phi by dr is equal to del phi dot r cap. Now, what does this expression say, or what does this equation say about the physical significance of the gradient of a scalar function? Now, as we clearly say that the gradient of a scalar function is a vector. So, how come this has become vector? Because we have a unit vector r cap along the displacement of the given scalar function. So, we can write this equation, thus we can write d phi by dr is a directional derivative, and the rate of change is maximum if r cap is along del phi, or else we can say the rate of change is maximum if r cap, the angle between r cap and del phi is equal to 0. So, that is how we can say that if we consider the gradient of any scalar function, it becomes a vector. By this equation or by this expression, we can write gradient of a scalar field phi is a vector field for which is equal to the maximum rate of change of phi and direction of which is same as direction of displacement along which the rate of change is maximum. So, this is regarding the physical significance of the gradient of a scalar function. So, which says that gradient of a scalar field is a vector field for which the magnitude is equal to the maximum rate of change of the scalar field and direction of which is same as the direction of the displacement along which the rate of change maximum. Hence, this clearly shows that the gradient of a scalar field is a vector field or the gradient of a scalar function is a vector function. One of the examples for this is an electric potential is a scalar function, but the electric field intensity is a vector function, wherein if you apply the gradient for a electric potential will give the electric field intensity. So, hence the gradient of any scalar function becomes a vector function. Next topic is divergence of a vector field. So, let us see what is mean by divergence of a vector field. In order to describe the divergence of a vector field, let us consider a vector field A, the magnitude and direction of which is a function of the position coordinates at a certain point inside that vector field. So, consider a vector field A, vector A, the magnitude and direction of which is a function of position coordinates at a point, then the scalar product of differential operator del and the vector A is a scalar function of position coordinates x, y and z is called divergence of a vector field. So, this is the statement for the divergence of a vector field. So, as I said, if you consider a vector A inside the vector field and which is the function of the position coordinates, both the magnitude and direction, then if we consider the scalar product of a differential operator del with the vector A, then the resultant will be a scalar function of the position coordinates, which we call it as the divergence of the vector field. Now, how can we express this in the terms of equation? So, you can write it as div A, or it can also be written as del dot A is equal to dou by dou x into I cap plus dou by dou y into j cap plus dou by dou z into k cap dot ax into I cap plus ay into j cap plus az into k cap. Now, if we consider the scalar product of these two, the differential operator along with the vector, then we will get dou by dou x of ax plus dou by dou y of ay plus dou by dou z of az. So, this is the equation form for the divergence of a vector function. So, as you can see, the resultant equation does not have any unit vectors along x or y or z axis. Hence, we can say that if you consider the divergence of a vector field, the resultant will be a scalar quantity. As you can see, there is no directional vectors along x axis, y axis or z axis. So, del dot A is given by dou x of ax plus dou by dou y of ay plus dou by dou z of az. So, this is what is meant by divergence of a vector field. Next topic is physical significance of divergence of the vector field. Now, in order to find out what is the physical significance, let us consider a vector field, and in that vector field let us consider a volume V which is enclosed by surface S. In that volume, let us consider a vector at a particular point inside the volume V, and let us draw a normal to the surface S. Let theta be the angle formed between the vector A and the normal drawn to the surface S. So, in order to find out the physical significance of that particular vector A, we will consider a small elemental surface ds at that particular point from which the vector is drawn, or from which the vector A is drawn. We are considering the vector A, we will consider the flux outside the vector field to the small elemental surface dx. So, flux of the field outside the area ds, A ds cos theta, which will also be written as vector A dot. Now, this is the flux outside the small elemental surface ds, but we want the flux through the whole surface S. So, the total flux through the whole surface is given by double integral over surface S vector A dot ds. Next, we can say if delta V is the volume enclosed by the surface is very small, then the outward flux per unit volume gives us divergence of vector A. So, if I consider the delta V to be the volume enclosed phase which is very small, then the outward flux per unit volume gives us the divergence of vector A, which can be written in the equation form as div A is equal to delta V tends to 0 1 by delta V double integral of S vector A dot ds. So, this is the general equation or general expression for the divergence for a particular vector. As you can see that from the equation, if you consider the divergence of a vector function, the resultant will be a scalar function. Now let us consider an example for this. For an electric field, the divergence is given by di V is equal to volume tends to 0, 1 by V double integral S E dot ds. Now this is the divergence equation for an electric field which is surrounded by a unit surface area at a particular point inside the volume. So di V is equal to limit delta V tends to 0, 1 by V double integral over surfaces E dot ds. Now if you consider the divergence of electric field at any point inside the vector field, which it will give us the charge density. So hence we can write the divergence of electric field at any point gives us charge density at that point given by del dot E is equal to rho by epsilon naught, which is a scalar quantity. So if you consider the divergence of the electric field unit surface area at a particular point, so we found out that the divergence of the electric field at any point inside the surface gives us the charge density at that point given by del dot E is equal to rho by epsilon naught, which becomes a scalar quantity. So hence we can say the physical significance of the divergence of any vector is nothing but a scalar quantity, or divergence of any vector field is a scalar field. Now considering the cases of an electric field as shown in both the figures, we can write certain conclusions from these figures. So what is the first point? If an electric vector or if an electric field vector, electric lines of force diverges from the point P shows divergence is positive indicating the presence of a positive charge Now in this case, or in this, the electric lines of force are converging towards the point P, or we can say the electric field E has negative divergence indicating the presence of a negative charge. Now, if the electric lines of force are diverging from the particular point P, then we can say that there is a positive charge at that particular point, and if the electric lines of force are converging, or we can say it has a negative divergence, then we can say it indicates that there is a presence of a negative charge. In a region, if the inward flux is equal to outward flux, then the divergence of that particular vector A is equal to 0. So, in that particular vector field, if the inward flux is equal to outward flux, the divergence of vector A is equal to 0, then is called solenoidal. Else, in other words, we can say if a vector field vanishes when it is undergone divergence, then it is called as solenoidal. Del dot B, div B or del dot B. So, these are the some of the properties based on the physical significance of the divergence. One is regarding the divergence and convergence of the electric field lines, and second one is regarding the flux, the inward flux and outward flux. If they are equal in a vector field, then divergence of such vector field becomes equal to 0, then such a vector is called as the solenoidal vector. Okay. So, this is regarding what is the physical significance and what are the some of the properties of the physical significance of the divergence of the vector inside the vector field.